Both section 5.5 as well as section 5.6 will have us factor problems that have just two terms, but they're two very carefully constructed terms. If I just randomly write down a two-term binomial, it's not likely going to factor. So in section 5.5, we have two categories of problems that are really very similar. So in this section, one of the categories of problems that we're going to wind up factoring is called a difference of squares. And a difference of squares is a problem that after any GCF is factored out, an expression is considered a difference of squares provided it only has two terms. If it has more than two terms, then can't be a difference of squares. There's a minus sign between because of the word difference. And any variables will have even exponents. Mostly when we're factoring differences of squares, the exponents are 2. That's probably 90% of the time. Occasionally, when we're factoring problems that fit the criteria for difference of squares, we'll see an exponent like 4, 6, or 8. Any numbers that are left after you factor out a GCF are perfect squares. And I wrote down the perfect squares that I know. 1 squared is 1, 2 squared is 4, 3 squared is 9. So this list of numbers, those are all perfect squares. If this is true, problem only has two terms, it has a minus between, the variables have even exponents, and the numbers are perfect squares, then it's super easy to factor. The template for factoring differences of squares is one parentheses gets a plus, the other gets a minus. And how do I fill in my parentheses? It's super easy. I square root any numbers, divide exponents by 2. Let me show you what I mean. If I look at 9x squared minus 16, and I was asked to factor it, it's two terms. There isn't a GCF. There's no greatest common factor to factor out. And this is going to meet the criteria. Look at this. It has two terms, 9x squared and minus 16, so it meets the first criteria. There's a minus sign between, it meets the second criteria. The exponent is 2, it meets the third criteria. And the numbers that I see are 9 and 16. Those are both perfect squares. So this problem, 9x squared minus 16, is considered a difference of squares. How do I factor differences of squares? It's so easy. I look at the first term. The first term is 9x squared. The first term is going to wind up being split evenly between the two parentheses. One parentheses with a plus sign, the other parentheses with a minus. How do I split it up? I square root the number, and I divide the exponent of the variable by 2. Square root of 9 is 3. X, when you divide its exponent by 2, you get 1. So the 9x squared gets split evenly between the two parentheses. I'll move on to the next part of this because I'm factoring 9x squared minus 16. I've got the first numbers, or the first terms in my parentheses inserted. How am I going to get the last terms? Whichever is after the minus sign. Square root any numbers, divide any variables exponents by 2. Square root of 16 is 4. So after my 3x's and the sign that I predetermined, I'll plug in 4's. When I talk about factoring differences of squares, I say we get two identical parentheses except the signs are opposite, because here you have one plus and one minus. If I wanted to check to make sure my answer is right, that 3x plus 4 times 3x minus 4 is a correct factoring of 9x squared minus 6, 9x squared minus 16, I would just FOIL. So I did firsts for my checking. 3x times 3x is 9x squared. Outers, 3x times minus 4 is minus 12x. Inners, 4 times 3x is positive 12x. Last, 4 times minus 4 is minus 16. Canceled the 12x's. I got 9x squared minus 16. That's exactly my original problem, so it's factored perfectly. So that's half of the section, other than we might have some GCFs thrown in. We'll factor out a GCF and then possibly 2 parentheses factor. But the new technique, not GCF is the old technique, the new technique, if we can identify a problem as a difference of squares, is to do exactly this. Make a template, 1 parentheses with a plus, 1 with a minus. Whichever term is written first, split it equally between the 2 parentheses by dividing variables of exponents by 2, square rooting coefficients, and split the last number up evenly into the last positions of each factor by square rooting any number, dividing any variable's exponent by 2. Differences of squares are easy to factor. The next category of problems in this section are sums of squares. And the only difference between a sum of squares and a difference of squares is the word sum. And to be a sum of squares, you need to meet all the criteria for a difference of squares except you have a plus sign. Specifically, after the greatest common factor is factored out, if a problem has only 2 terms, instead of a minus between, a plus between, variables with even exponents like x squared y to the 4th is e to the 6th w to the 8th, and numbers are perfect squares, then it's considered a sum of squares. So on this sheet I said factor y to the 4th plus 25. Let me show you that it's a sum of terms, squares. It only has 2 terms, check. There's a plus sign between the terms, check. The exponent is even, check. And the number given is a perfect square, check. That's a sum of squares. Sums of squares don't factor. They're all prime. They actually factor with i's, if you believe it or not, but they don't factor. So if I was asked to factor this, if I identify it as a sum of squares, sums of squares don't factor. They're all prime. Let me try to show you. I don't have so much scratch paper here. Let me show you on the sheet that I've worked with already some common mistakes. So difference of squares factor all day. Here's an example of a simple sum of squares. It's going to be prime. All sum of squares are prime. To be a sum of squares, you need 2 terms. You need a plus sign between the terms, and the exponent is even, the numbers are perfect squared. The common mistakes, because this is prime, the common wrong attempts to factor rather than just saying prime. Real often I'll see students say something like x plus 3 quantity squared factors into x plus 3 squared because they think you could just square the x and square the 3. But this isn't right, because if I try to check it, I rewrite it without the exponent and I FOIL. I do x times x, x times 3, 3 times x, and 3 times 3. And I don't get the original problem. I get x squared plus 6x plus 9. It has that extra 6x. Similarly, sometimes students will try to be sneaky and say x squared plus 9, which is prime, factors into that. But if I multiply this out, firsts are x squared, outers are minus 3x, inners are minus 3x, lasts are plus 9, it would multiply to that. Some students will write this. Firsts are x times x, x squared, outers x times minus 3x, inners plus 3 times x plus 3x, lasts 3 times 3 get minus 9. And that doesn't match up because it has a sign issue. There's nothing you can do to make a sum of squares factor unless you knew how to factor with i's. I don't think I've ever factored with i's, but it actually factors. This actually, if you allowed i's and you FOILed that, that would equal x squared plus 9. but we're not in the world of imaginary numbers here. I'm not going to even show you that that checks. That's way too heady for our class right now. We're just going to call all sum of squares prime. Differences of squares, factor into two essentially identical parentheses, sum of squares, all prime. So when I look at problem 2, I see the minus. So the criteria to be a difference of squares, it needs two terms. Good. If it has a minus, it's a difference of squares, and it factors. If it has a plus, it's a sum of squares, and it's prime. The difference of squares, if it turns out to be a difference of squares, you'll get two identical parentheses except for the signs. But I don't know that it's a difference squares just yet because I haven't done the real important checks. Any variable needs to have an even exponent. 2 is an even exponent. And the numbers need to have integer square roots or be perfect squares. That's not even readable. The even exponent is good, and the square root of 81, if I pulled my calculator out, it would be 9. So it is a perfect square. So if this is a difference of squares, let me go to factor this. I'm going to make two parentheses. One's going to have a plus sign, the other's going to have a minus sign. I'm going to take the y squared, I'm going to divide its exponent by 2, and I'm going to split it evenly in the first position in each parentheses because the y squared is written first. When I divide that exponent by 2, I get a y to the first that I'm going to put in the front of my parentheses. And now I'm going to square root the 81. I know that, so I'm not going to pull out my calculator. This is checkable, but I'm not going to check it right now. Done with number 2. Number 4, it's the same problem with a plus, which makes it a sum of squares. To be a sum of squares, you have the 4 criteria. 2 terms, plus between, even exponents, and perfect squares. I have 2 terms, plus between, exponent is even, and 81 is a perfect square. All sums of squares are prime. Six is a difference of squares. It has 2 terms. The minus between, even exponent, 2 is the exponent and it's even, and numbers that have nice square roots. Perfect squares have nice square roots, and the square root of 49 is 7. It reduces and it doesn't have a square root in the reduction. Because this is a difference of squares, it's going to factor. I'm going to get 2 identical parentheses, one with a plus sign, one with a minus sign. The exponent of the b I'm going to divide by 2, get a b to the first, and split that evenly between the parentheses in the first position. 49 has a square root of 7. I'm going to split that between my parentheses in the last position. 8, I changed the letter to x as opposed to b, but this is a sum of squares. Has 2 terms, plus between, even exponent, and 49 is a perfect square. A sum of squares is always going to be prime. Let's do 9 and 11. For 9, I look at this problem. 2 terms, good. That makes it possible for one of the categories. The minus between makes it likely a difference. The exponent is even. And each of the numbers is a perfect square because when you square root the 25 and you square root the 81, you're left with an integer. So this is going to factor, it's a difference of squares. So when I go to factor number 9, I'm going to make 2 parentheses. I usually put the plus in the first parentheses and the minus in the second, but it doesn't matter. For the first position, I'm going to square root the 25, and I'm going to divide the exponent of the a by 2. When I square root 25, I get 5. When I divide the exponent of the a by 2, I get a to the first. Those are going to load up my first positions. After the signs, I'm going to square root the 81, and get 9. And that's the answer. That will check. Problem 11 is kind of the brother of problem 9. It's a square problem, but it's a plus. It's a sum of squares, and sums of squares are always prime unless you know how to factor with i's. I'm going to skip 13, 14, 15, and 16. They're essentially the same, and get to the problems that have the common factors because they're important. So in problem 17 and 18, there's a common factor that I need to factor out first. I'm going to start with problem 18. Both terms have an x, and when you have a variable in common, you take the smaller exponent. The smaller exponent is the x cubed. I'm going to factor out my x cubed, which means take 3 x's away from the x to the 5th and be left with an x squared. I'm not factoring out a negative, so I'm not changing any signs. After the negative sign, I didn't factor out a number, so I still have the 121, but I took the entire x cubed away. What's left in my parentheses is a difference of squares. Specifically, inside my parentheses, there's 2 terms, a minus between. The exponent is 2, so it's an even exponent. And the number 121 has a perfect square root. So it's a difference of squares inside the parentheses, and it's going to factor. One of the parentheses will have a plus, the other will have a minus. To lead up my parentheses, I'll take the x squared and divide its exponent by 2 and get x to the first. Split that equally into the first positions. To finish up my parentheses, I'm going to square root the 121 and split that equally. So that's the answer for 18. It would be wrong if I just quickly said 20 is prime, because anytime you could one parentheses GCF factor, your problem isn't prime. You could at least one-step factor, and problem 20 has the same one-step factoring that problem 18 has, because the only difference between problem 18 and 20 is the plus sign. Everything else, the terms are the same. And the difference between 18, where I was able to write 3 factors, and 20 is a 20 I can't go further because what is left is prime. So the answer for 20 isn't prime because I'm able to factor it, but I just can't go further. I GCF factor and stop. Let's do 21 and 23. So for 21, I'm going to pull out the common factor of 3. When I pull out the common factor of 3, I'm left with x squared minus 9. X squared minus 9 is a difference of squares, 2 terms, minus between, even exponent, and 9 is a perfect square because its square root is 3. So I'm going to break the x squared minus 9 into 2 parentheses. I'm going to divide the exponent of 2 on the x by 2 and get x to the first. Split that evenly up into the first positions. At some point, put a plus sign in one parentheses and a minus in the other. And after the signs, the square root of 9 goes, which is 3. 23 is again kind of the sister of 21. They're the same problem other than the sign is plus as opposed to minus. It has the same first step that I could factor out a common factor of a 3. But what's left is a sum of squares, and I can't go further. So the answer for 23 is going to be that 3 times the quantity x squared plus 9. 25 and 26 aren't written in a very nice way because there's a negative up front. I need to factor out a negative 1. If the first term is negative, I almost exclusively either factor out a negative 1 or I factor out the opposite of GCF. There's no GCF in problem 26. So when I factor out a negative 1, the signs are going to flip. the negative 16y squared is going to turn to positive 16y squared. The positive 49 is going to turn to negative 49. I don't know why there's such a gap between the negative and the number, but it is what it is. Maybe I'll try to fix that in these problems here in a minute. After I factor out the negative 1, in problem 26, I'm left with a difference of squares because the numbers are square rootable, the exponent is divisible by 2, and there's a minus between. So I'm going to fill up my parentheses with square rooting the 16 and dividing the exponent of the y by 2 to lead off my parentheses. Square rooting the 49 and getting a 7 to end up my parentheses. 28, same deal. I'm going to factor out a negative 1. I could just write a negative sign if it bugs me to have the 1. I like the 1, but it's not necessary. In 28, because the first term is negative, I should probably factor out a negative. Now I might need my calculator to make sure this is a good thing. Let me square root 144. That's good. Square root of 144 is 12. And let me square root 121. Also good. The numbers are perfect squares because their square roots are integers. So I'm going to break this into two parentheses. One with a plus sign, the other with a minus sign. The first positions get a 12 and an x because you square root the 144 and divide the exponent of the x by 2. The last position, you get the 11 from square rooting the 121. Let's do, I just did odd problems, or did I just do even? I just did even. Let's do the odd problems on this sheet. For 29, it's a difference of squares. The exponent is even, there's a minus between, 9 has a nice square root. I'm going to create two parentheses, factor it. To fill in the firsts, I'm going to divide 4 by 2 and get a couple of x squareds before my signs. To end off my parentheses, I'm going to square root the 9 and get a couple of 3's. 31 and 32 are the same, so I'll let you do that if you want to give those a go. Rather look at 33 and 34 because those look harder to me. Multiple variables, larger numbers. Let me try 34. In 34, both 50 and 128 are even. I'm going to factor out a 2. I'm going to write a 2 in front of my parentheses. And then to the left of the minus sign, because I'm not changing signs, I didn't factor out a negative. 50 divided by 2 is 25. I can't factor out an x because the second factor doesn't have an x. When I factor out a 2 from the 128, I divide the 128 by 2 and get 64, and I leave the y squared. So it's still a difference of squares because numbers have nice square roots, exponents are even. Ultimately, I'm going to break this down into two parentheses, one with a plus sign, one with a minus sign. Before the signs, I need to work on the 25x to the 4th. I'm going to square root the 25 and get 5. I'm going to divide the exponent by 2 and get an x squared. So preceding my signs, I get a couple of 5x squareds. Following my signs, I need to square root the 64 and I need to divide the exponent of the y by 2. Square root of 64 is 8. When you divide the exponent of the y by 2, you get y to the first. So following my signs, I need a couple of 8y's. Be beautiful if you tried 35, 37, 39, have tricks. The only trick that I know in factoring differences of squares. Sometimes differences of squares double factor. I never put those on a test, but some teacher may in a higher class. So for 35, it's a difference of squares. The exponents are even, numbers have square roots. Let me do my work here. For the x to the fourth, I'm going to divide its exponent by 2, split it evenly between my parentheses. The 16 has a square root of 4, split it evenly in the last part of my parentheses. If you checked my key for 35, my key for 35 says x squared plus 4, which is a sum of squares, which is prime, times x plus 2 times x minus 2, because the second parentheses is still a difference of squares. It has an even exponent on the variable, 2 terms with a minus between, and 4 is a perfect square because the square root of 4 is 2. The first parentheses is a sum of squares, it's prime, but the second parentheses, I can go further. This is the big trick. When the exponent starts at 4, sometimes you can double factor, and this is the case here. I can double factor the x squared minus 4, get a couple of x's to lead off my parentheses by dividing the exponent by 2, and end my parentheses with a couple of 2's by square rooting the 4. I think the next two problems that we're going to look at have that same trick, and a common factor to boot. Problem 38, the numbers are ridiculously large because to make this trick happen, mostly I need large numbers. And number 38, I'm going to factor out a 2 because both 2 and 1250 are divisible by 2. And when you factor out a 2, I'm going to be left with x to the fourth minus 625. Anytime I see a difference of squares with an x to the fourth and a particularly large number after the minus sign, it's probably a double factor problem. To do the first level of factoring, I'm going to take the exponent of 4 and divide it by 2 and get a couple of x squared, which makes it another square problem. To finish off my parentheses, I'm going to square root that 625 and get 25. My first parentheses is a sum of squares, it's prime. My second parentheses is a difference of squares because it fits the criteria. Even exponent, 2 terms, minus between, number has a nice square root, or the number is a perfect square. So that second parentheses, I'm going to divide, split the x up into the firsts of the next two parentheses that I wrote, and split the 25 up between the parentheses that I wrote. Let's do 39. You need a calculator, or I need a calculator. It's a difference of squares. The square root of 2401 is 49. So for 39, I divide the exponent by 2, front off my parentheses with my y squared. One parentheses gets a plus, the other gets a minus, and they end with 49 because that's the square root of 2401. First parentheses is a square with a plus. It doesn't factor. But the second parentheses is a difference of squares because the exponents are even and the number has an integer square root. So I'm going to break that y squared minus 49 into y plus 7 and y minus 7. That's considered completely factored. I never put that trick on a test, but just in case when you're in college algebra, assuming you take college algebra, that trick comes up, at least you've seen it before. Last two problems, the plus sign between these and the fact that they're square problems makes them sum of squares. It's a sum because of the plus sign. It has even exponents. The number 9 has a nice integer square root. It's a sum of squares, and sums of squares are prime. 30 minutes, I guess it is what it is. I wouldn't want it to be any longer, so we'll stop here and we'll move on to the next section, which is factoring cubes, which are similar but oddly different than squares.